Okay, we like to find the shear force and bending moment distribution along the beam ABC. The first step is to find the ground reactions. So to find the ground reactions, I'm going to draw the free body diagram. At point A, I have AY or FA, whatever you want to call it. And then at this point, I have CY or FC. And then I have a CX, which is 0 because you don't have any forces on X. The resultant will be 0. One external moment here as 80 kilonewton meter. In the middle, we have here 1.5 or 15 kilonewton. A distributed load located here with intensity of 5 kilonewton per meter. And the distance from here to here is 5. So you need to replace this with 1 point force. It's going to put it on the middle. And the middle will be like distance of 2.5 from here. The amount of this is area under the curve. So 5 times 5 will be 25. 25, again, look at the units, right? Kilonewton per meter, meter. So the answer is going to be kilonewton. Sum of f of y equal to 0. This will give me ay plus cy is not 0. Ay plus cy minus 15 minus 25 equal to 0. So ay plus cy is equal to 40 kilonewton. Let's keep this for now. The second equation I have, I'm going to do a moment about point A. Sum of moment about A is equal to 0. So we got 80 there, which is a minus 80. It's going to go clockwise. And then I have the 15 kilonewton. So minus 15 kilonewton, that's clockwise too, times the distance of 5. The perpendicular distance from that force to the point A is 5. Next one is 25, so I have minus 25. The distance for that is, you have a 5 there, you have 2.5 there, here. It's going to be 7.5. And then plus cy, that's a clockwise moment. The distance for that is 10. So if I simplify this, I'm going to get cy is equal to, okay, bear with me, 80 plus 15 times 5 plus 27 times 7.5. I got 357, and then if I divide that by 10, I'm going to be 35.75. That's going to be for the cy, kilonewton. Ay, I can actually calculate the ay to see how much the amount of ay is. So ay plus cy was 40, and ay would be equal to 40 minus this value, 40 minus 35 point, it's going to be 4.25 kilonewton. Okay, we found the ground reaction after a while. So let's start with the cut. The first cut would be from here to here. Because there is nothing in between, I can do a cut there. So if you do the cut from here to that location, this distance is x. At the point A, we have 80 kilonewton meter as external moment. We have a ground reaction at 4.25 kilonewton. And at this location, I have a V and I have an M. V stands for the shear force, M stands for bending moment. When you do the cut, there is a normal force to it that we don't consider it because there is no force in the horizontal line. So sum of f of y equal to 0. From here, I have V plus 4.25 equal to 0. And then you will end it up as V is equal to minus 4.25. Perfect. This is actually a check mark for perfect, but the unit for this is kilonewton. That's the unit for it. So sum of moment about point A is equal to 0, or I can do about point C here. C is already used. Let's use point D here. Sum of moment about point D equal to 0. From here, there's nothing for the V to be worried. I have 4.25. That's going to go clockwise moment. So 4.25. The distance from here to here is x into x. and that's a clockwise moment. M is positive. M is just the bending moment, and then minus 80. So from here I'm going to get M is equal to 80 minus, this will be plus 4.25 x. That's or bending moment anywhere that we cut between A and B. I'm going to cut, the next cut that I do is after the 15 kilonewtons, somewhere in here. That will be my second cut. So if I do a cut at that location, I have something look like this. I got the 80 kilonewton here. That's the external moment, the force of 4.25 kilonewton. You have it there. From here to here, again, immediately at this point, at this location, we have a 15 kilonewton. And after that, we have the uniform loading of 5 kilonewton per meter. The distance from here to here is x. So we need to figure out our equations. Again, where we cut it, I have to put a v there, and I have to put an m there. So sum of f of y equal to 0. I'm going to have v minus 15. Okay, this one I need to convert it, right, to a point force. So the height is 5. The base is x minus 5, right? This base here is x minus 5. And the amount of load is 5. So this will be replaced with 1 point force. And that point force will be in the middle of 5 into x minus 5. So if you simplify this, this will be 5x minus 25. 5x minus 25, that's the force that's going down in the middle here. So v minus 15, okay, minus 15 was this, minus 5x plus 25. Remember, because it's going down, that's why the whole reason I just changed the number for it, right? It came minus 5 plus 25, and then plus 4.25. If I simplify this, I'm going to get 4.25 plus 25, and then we have a 15 there, so this will be 10. So 10 plus 4.25 will be 14.25. So V will be equal to minus 14.25 minus the 5x. Or something of this would be positive. So let me just to check. This will be minus. And this will be a 10. Yeah, so this will be the V. Again, I'm sure I have an error somewhere here, but it's a 15 going down, 4.25 going up, and then this is 5x minus 5. If you put again x is equal to 6, 5 minus 5x plus 25, this will be a 10. Yeah, so this is what I got for the V. Then I can repeat the same equation for the M. So for the M, I'm going to get sum of moment about point, like for instance, O is equal to 0. Point O is here, by the way. So I got the moment at that location. V doesn't have moment. This one has a positive, and then this 4.25, a negative, and this is a negative. So I'm going to get M plus 5x minus 25. That's multiplied by distance of half of that, right? Times half of x minus 5. The next one, I have the 15. So for 15 plus 15 into x minus 5, and then plus 4.25. The 4.25 is going negative, so this will be a minus because that's a clockwise moment. The distance for that is simply x, and then the AD is negative. Minus AD is equal to 0. So I'm going to get a little bit longer equation for this. I can simplify this equation and I can use it along with this to draw my diagrams.